I will discuss about one specific approach I propose for big data analytics. And in the second section, I briefly touched some of the optimization topic, which means evolutionary intelligence for optimization. I briefly talk about techniques and then some applications. And finally, if find time, I can talk about some heuristics. So first, evolutionary intelligence or evolutionary computation for data analytics. So in data analytics or modeling tools, we are all familiar with AI as a big portion of these areas, yes. Machine learning techniques, neural networks, including neural networks, fuzzy logic, support vector machine. And here we specifically want to focus on one techniques that you may haven't even heard about, called genetic programming. And I will explain why we recommend these techniques and where and how it could be useful. So when we want to do data analytics or data mining, we have two main selections. We want to do feature selection, and then we need to do model selection. For example, here you can see this plot for feature selection. We need to find optimum number of variables. For example, for this problem, the optimum values was placed here. Or after doing some pre-processing, we would like to find the best model. For example, if you see in this classification problem, this is the ROC plot. Most models was very close to the random. Yes, you can see none of the model can reach to the acceptable degree of accuracy, but eventually one model, which was XGBoost, outperformed all other models. So model selection is also very important in machine learning and predictive data analytics. So after saying that, let's start evolutionary computation. So in 18th century, Darwin proposed the theory of evolution in his well-known book on the origin of species. And I should say evolutionary intelligence is slightly different from classical artificial intelligence, because here intelligence comes from the nature. It's not like a other classical intelligence, which mainly only comes from human. This could come from any natural element that evolved during the times. So following this principle of Darwinian selection, genetic programming tries to create programs in order to find a relationship between inputs and output. So unlike any other evolutionary process, it has a loop, which we call it in mathematics we call it iteration. Here we can call it generation in evolutionary computation. So in each generation, we have several evolutionary mechanisms such as selection, crossover, and mutation, and then go to the next, creating the next generation. So a genetic program can be translated into the tree form like this. So as you can see, it can have a mathematical operator like here, or variable, or constant values. Now, each of these programs or trees can be considered as one individuals. Crossover can happen between parents, and mutation could also happen in one individual tree or multiple trees. So, but as I mentioned, why genetic programming? This is main question that we need to answer. So I should say it's genetic programming really different from other machine learning techniques because predefined structure is not required in this method. So in every other method, even looking at the regressions, neural networks, any fuzzy networks, SVM, you need to define a structure for it. For example, in neural network, you need to define a number of layers, number of neurons, I don't know, activation function, etc. And then eventually find some coefficient for that network. But here we don't have any predefined structure. So we ask evolution to find the structure of the model, which means we need to build a model from scratch. We don't have any structure defined for us, like network or um, layered network, etc. So this makes a problem harder because we need to find the structures, but it makes the model much more flexible, which means we try to fit the best model during evolution to our problem or to our data. And there are some other advantages, like it doesn't need pre-processing like normalization or standardization that others may need, or it can model behavior without any prior assumption. The other most important thing is the model is relatively short and simple, and I should say it's very transparent. So in the era of all these transparency and ethics, if we have a model that we can look into it, it's a closed form solution, it would be very, very worthwhile. And because of these actual features, it's been widely used in some engineering problem, like civil engineering or mechanical engineering. And the other thing is genetic programming can select the features. As I mentioned in the beginning, I said in the data analytics, we need to have two main selections, yes? One feature selection, one model selection. So genetic programming can select features inherently, and also it doesn't have any predefined structure. So sort of it can do both those selection inherently in its process, which is very, very interesting. And the other thing is, if you say, okay, it looks like a very, very big problem. Does it even work? Does this algorithm even work? And I can say yes. And so many people already apply it to very complex real-world problems. For example, NASA, not recently, about 15 years ago, they used genetic programming for designing their communication antenna for the ST5 mission. Another feature of genetic programming which distinguishes GP from other machine learning techniques is it's a population-based method, which means instead of maybe randomizing or seeding one initial solution and try to optimize that single solution, it try to work with a population of solution, which is very interesting for this method because in this era of a distributed system and parallel processing, it could be very, very interesting to implement genetic programming parallelly. Actually, I think I should say most people in this area use parallel GP because, and they can take advantage of this cloud system, parallel system, and distributed system in general. So let's start from the first example. This is the real world and very complex problem. So this is a very complex structural system. You can see it's not similar to the regular structural system. It has, for example, post-tensioning bars that connect the roof to the ground. It has some, it has adjacent column. It has some load bearing or energy dissipation element. And when it's under lateral load, you can see one of the column can uplift from the base. So the system has a very complex behavior. And this is the, for example, roof drift of this structure during a Mangil earthquake. So what we want to predict from this system is its maximum roof drift or maximum response from during earthquake. So we want to predict this point. So considering the complexity of the system and also the stochastic nature of an earthquake, this could be a very difficult problem to solve. So I should say for making prediction for this problem, we need some structural element, features such as geometrical or mechanical features of the system, and also some intensity measures of earthquake. So I have listed 14 of them here, and I should say they are much more than this. It's more than 35 I've seen there listed in one paper. Anyway, so these are our variables for these problems. And for prototype structure, we considered one office building designed for a stiff soil site, and it's located in LA, California. And this is the system we want to analyze. So I've considered three elevation for this problem: 4-story, 6-story, and 8-story buildings. And these are the earthquake applied to this structure. They are all in dBE level. And these are the earthquake, actually 30 earthquake here, and 140 different earthquake records here. So total 170 earthquake applied to the structure, and 75 different structure have been considered here. So we create a decent database for this problem. And one interesting approach that we used in this study is we are familiar with correlation coefficient, yes? The correlation coefficient can give us linear relationship between two sets of data. But this is the problem, because this is the linear relationship. Sometimes we don't have this linear relationship, and this relationship becomes nonlinear. So we try to improve the correlation coefficient using genetic programming, and I call it evolutionary correlation coefficient. This is the formula. You can see we embed GP in the system. And this is the improved correlation coefficient. So in this column, you can see the regular correlation coefficient, the classical correlation coefficient, and here you can see evolutionary correlation coefficient. So comparing these two, you can see in some cases we have a very, very high advantages by using this system. So here you can see you have 352% improvement in the system. And eventually, based on this evolutionary correlation coefficient, we select 3 of these earthquake intensity measures. So we use it as a feature selection. And we tried put all genetic programming models in one pool. We find the Pareto fronts, these green dots, and eventually we select this model as the final model. Why we select this one? it's clear, because going to the right, complexity increase, but we don't have that much increase in the accuracy. This is the accuracy, this is the complexity. So eventually we find this. I outline all of these details in the related paper. So this is the very, I can say, simple equation for such a complex problem, which was very exciting for us too. And these are the final results. You can see it's a very high correlation coefficient for both single objective case and multi-objective case. The next problem that I can discuss is one well-known problem in engineering. So if you know, in engineering, we usually do forward analysis. Yes, we have a system, we put some input in the system and it gives us output. This is a forward analysis. But sometimes, mostly after designing the system, we have the inputs and we have the outputs of the system, but we don't know system parameters. For example, we don't know if our system...
Hello, Professor.
Yes.
Your slides are not visible.
Really? Okay.
Yeah.
Okay, let me see. Let me reshare it.
Yeah, now we can share.
That's weird. You can see it right now?
Yeah. Now, yeah, wait.
Did you see it?
Yeah, yes, Professor. Now it's okay.
Okay, so hold on, I can. Okay, so sometimes we need to do inverse analysis in engineering, which means we don't know what happened to our system after some time. If the system is intact, if it is damaged, if its parameters changed, some environmental effect changed the system, etc. So this problem in inverse analysis is very complex. And I can say nearly in most cases, we don't have any solution for inverse analysis. So this is some place that we can use and take advantage of evolutionary computation and AI in general. So there is one framework actually proposed by Professor Gabushi at UIUC. So they run two parallel finite element analysis. One of them is force control, the other one is displacement control. And they create a database, and then they train a neural network in each iteration. They continued all this process in a loop in order to develop one ANN based or artificial neural network based constitutive material model. So what I did in here is, okay, I said if we have an unknown material and we want to build a constitutive material model, neural network probably is not a very good option. Why? Because first, it's very complex, taking derivative and these things from it. It's a real problem. And also, it's usually a black box problem, and we don't know even detail of this system. We want to construct a Jacobian matrix, and etc. And we cannot even put this system in a user-defined material like Abacus or ANSYS. So what I did, I simply replaced this neural network with genetic programming. And as I said, genetic programming can be easily translated to a closed form solution. So this is genetic programming and eventually a simple formula for a constitutive material model, which we can take derivative, we can use it as a Jacobian matrix, etc. So this is one case study that I solved. This is the cantilever beam with two forces at the end of the truss, and this was the force displacement curve, and this is the results by Professor Gabushi's method, neural network, and this is my program, genetic program, and this is eventually the results of genetic programming versus experimental results. You can see they're almost identical. And this is the final results after implementing my model in an Abacus software. Because now I have a very simple mathematical formula. I can simply write it down in any software as a user-defined material. So that's what I did. And this is the reference model, and this is the genetic programming-based model. You can see the models are almost identical, and it's the GP model is very similar to the reference model, which was the Ramberg-Scott model. And I also solved some other cases like soil modeling and aortic modeling, but there's no time to go to the details. And this is another problem which I think it's interesting if you work on, for example, complex material problems. So here we will use a hybrid genetic programming, hybrid of genetic programming and simply linear regression. So you can see 3 genes are linearly connected using multivariate linear regression. And these are, for this problem, concrete creep prediction. And I should say, these are very complex engineering problems. So, for example, Bazant proposed a model for it, SEPFIB Institute proposed a model, or GL in 20 proposed, 2000 proposed a model for it. And these are the number of variables used in the model. And you can see, comparing the errors and correlation, our model is much better than others. Our model is called GC. And it outperformed all other models nearly in all cases. Or in another case study, we try to monitor student performances for a MOOC. Probably you're familiar with the MOOC, it's online courses. So they put a headphone with an overhead scanner for each student, and they try to see if the students learned what was taught in the class or not. So very simple classification problem. You can see this is the results of different models, LSTM, CNN, SVM, naive bias, etc. And GP could outperform all of these models with a very high degree of accuracy, 90% accuracy for this case. Or this is another case which NASA is also interested in. It is airfoil self-noise prediction. So there are some analytical models for this problem, like Brooks, and there are some machine learning model developed for it, like random forest, decision tree, lasso, etc. But GP in this case can also outperform the others. Or, for example, last year around this time, we tried to predict COVID for India. And this paper actually published about a year ago. So we try to say what's going to happen in India in the future. So we developed some time series forecasting model for India, and you can see the results. And GP seems to perform very well at that time. Okay, so moving fast forward for genetic programming in big data analytics, I should say, because genetic programming in 10 to 5 structure for the problem, the search space is so huge. So one of its difficulty is implementing it for big data analytics. So what I proposed in 2011, actually about 10 years ago, is we can decompose a problem to several one-dimensional problem, and eventually we can try to use function in order to model interaction between variables. So this is how we come up with the procedure. I won't go to the detail, but for each of these functions, we can find one system to model the problem. But several one-dimensional problem, for example, let's say 100 one-dimensional problem is much easier than 100-dimensional problem. So we have been very successful in solving big data analytics problem using this approach. So this is one case. This is not very big data problem, but it's an interesting case. It's a soil liquefaction modeling.
Speech ಮುದ್ಮೇಲೆ ಇದು.
Hello? Yes. So here, for example, MSGP, it's compared with the 3 state-of-the-art genetic programming, linear genetic programming, gene expression programming, and multi-expression programming. And you can say our proposed approach can outperform others in this case. And even without interaction, and with interaction, it has a very high accuracy. So we compare its results in order to apply it for big data analytics. You can see this is a GP performance, and this is the MSGP performance. It can converge much quicker in this case. And there are some other approaches when we combine genetic programming with other problems. I don't want to go to detail because I would like to quickly talk about evolutionary computation for optimization purposes. So talking about evolutionary optimization algorithm, I should say there are some classical optimization algorithm, and there are some other sort of optimization algorithm which use do not use derivative information, or they are derivative-free optimization algorithms. So most of these algorithms inspired from nature. So they use other source of information like evolution, swarm, or annealing, or this kind of information. So these algorithms are global, and they cannot trap in local minima very easily, and they usually use as random variables. So they could also be considered as a sort of a stochastic optimization algorithm. So there are some algorithms which are already very well known, and you can find them in everywhere in Python, in MATLAB, global optimization toolbox, etc., like genetic algorithm, simulated annealing, and particle swarm optimization. And there are some others that proposed recently. I've listed some of them here. I've contributed in some of these algorithms. Actually, I proposed Quillherd and interior search, and I contributed in the first paper of South Swarm or marine predator, and I also work with the other algorithm. So I won't go into the details of this algorithm, but if you are interested, please feel free to email me. I can share the code of all these algorithms. Okay, I should say these are not new algorithms. Boeing used genetic algorithm in 1998, or Hitachi used it for designing the nose cone of the train in 2005. And we also use those for very complex problems. For example, We use P3 algorithm, which proposed by Dr. Goldman, my colleague at Michigan State University. He's currently, I think, at Google. So we applied this P3 algorithm for a very large scale tower problems, 35-story space tower. You can see the number of members or number of degrees of freedom was very high. And we compared this algorithm with two state-of-the-art, and you can see how it can outperform these two algorithms. And the other application of evolutionary computation is for multi-objective or many objective optimization problem. And I should say most real-world problems are many objective or multi-objective. We want to optimize cost, minimize cost, we want to maximize quality, we want to minimize risk, we want to maximize reliability, and this sort of thing. So in this study, which recently published, we try to compare these three well-known problems, knapsack problem, traveling salesman problem, and quadratic assignment problem, with 3, 5, and 10 objectives. And we solve all these problems with 18 evolutionary many objectives problems. So this is a very interesting algorithm if you want a study, if you want to deal with multi-objective or many objective problems. And one real-world application of many objective multi-objective evolutionary algorithm is our results for pandemic challenge. Actually, there was a challenge by XPRIZE and Cognizant. So we wanted to try to minimize the number of daily new cases and also optimize a stringency of planned intervention. So these were two objectives. And I led the team Congress in this competition. And we used evolutionary multi-objective algorithm for these purposes. And we eventually came up as a finalist and top 10 team and won an honorable mention winner in this competition. And finally, I should say, I talked about the advantages of these algorithm, but I should say compared to mathematical algorithm, evolutionary algorithm is usually slower, but we can make it not only much faster, we can also make it much more effective if we embed our information into the process. You cannot touch the mathematical optimization algorithm, or at least you cannot tweak them a lot. But in evolutionary computation, you can embed your information, and if you find a way, it may outperform your results significantly. So I should say these algorithms are very flexible. There is no time to go to the detail of case studies, but actually I have one tutorial at IEEE Congress on Evolutionary Computation in about a month. So over there, I'm going to talk about how we embed our knowledge, like engineering information or expert knowledge into the process, and how we can boost our results. That's why we always propose the researcher to not use this algorithm blindly, try to consult with the expert in this sort of algorithm before applying those. So this is a topic that could be very interesting for the future. So there are some case studies. I can pass this. I think go through this about how we can embed our information. And conclusion, I should say first, these algorithms are not very complex evolutionary computation. You can simply code this algorithm if you are even familiar with this algorithm. And most of these codes are already available. But these algorithms can solve very complex problems. And I should say each of these algorithms could have advantages and could be strong in one sort of problems. Like this FA could be very good for multimodal optimization. ESA could be good for discrete optimization, or P3 could be good for large scale discrete optimization. And eventually, as I said, try to use heuristics and find a way to embed your information into the evolutionary process, which can really boost your algorithm. So this is, there are some positions available. Unfortunately, because of the pandemic, there's some difficulty for travel, but feel free to reach us out, and we will be happy to be in touch with you. And finally, thank you all for having me, and I will be happy to answer if you have any questions. Thank you.
Thank you very much, sir, for sharing your knowledge with all of us. All the participants are requested to give the feedback. The link has been shared in the chat box. Filling the feedback form is compulsory to get e-certificate.
Sir.
I now request our principal, Dr. M. Shivkumar, sir, principal of GSSS IETW, to moderate the session.
Thank you. Hello, sir.
Hello.
Sir, how this evolutionary computation or your genetic programming is being used in the pandemic outbreak?
Yes, actually, this is a very good question. I myself did some research on modeling of, for example, number of cases or number of deaths using genetic programming. So we try to build some time series forecasting model, and this is one study that we have done for COVID. And the other study that we done, the one I said led us to the top 10 team in the pandemic challenge, is we try to create a system that gives us the best policies in order to reduce the number of tests, cases, and also have the less economical impact. So because we always have different objectives, yes, if we there are some economic objective and there are some lives objectives. So we try to, for example, optimize these two objectives at the same time. So for that case, we built some machine learning cases for the number of machine learning model for number of cases, some models for stringency, and then we try to use evolutionary multi-objectives algorithm in order to find a best trade-off between these two objectives. And what we did, actually, we proposed dynamic policies, which means we can change the policies every month. So sometimes we need to close the borders, sometimes we need to close the schools, sometimes we need to open their schools and open the borders. So with this policy or measurement optimization was a very interesting approach that we did using evolutionary computation. And of course, in a medical sense, there are several prediction can be done using machine learning and AI, and also GP. I have seen several studies, and we also done some studies in these areas, but none of them have been published. But this is another area that people trying to use AI and GP and other evolutionary and machine learning algorithm in order to combat with this COVID-19. I cannot hear you. Hello?
Hello, sir.
Yes, I can hear you.
Sir, which is the language, programming language that's widely used? It is a Python for using genetic programming.
Good question. So we have C, we have MATLAB. Python is also available in some packages, not scikit-learn, but in some packages, genetic programming is available. I think you can find it in the most popular programming language, MATLAB or Python. I'm not sure with R because I haven't worked with R, but Python definitely has it, and C has it, and MATLAB has it.
How do you reduce the computational overheads in the genetic programming?
Yes, actually, these are very good questions. So one of the main challenges in genetic programming is it works very well for low dimensional problems. So if you have a low dimensional problems, I highly recommend you to use genetic programming. But if you have a very complex and high dimensional problem, probably GP will have some challenges. So one way of doing that is try to seed the model or give some information regarding the problem structure to the model. So one way could be this divide and conquer. Yes, divide the big problem to several smaller problems, or could be seeding some model into the system. So there are some ways like this in order to help the GP in order to construct the model structure. And the other thing is, as I said, genetic programming is a population-based approach. So you can easily use it for with a distributed system or multi-core laptops, or if you have access to cloud, you can very easily parallelize genetic programming and take advantage of those systems.
Any other specific research problems you suggest, sir, using
Yes,
the
so,
genetic programming?
So as I said, genetic programming is very good in order to find the structure. So, for example, finding the structure of when we have any ideas about the topologies of, for example, a truss structure or neural network structures, or when we don't have any ideas about those structures, genetic programming could be very, very effective too. So these are the areas that you cannot use other machine learning. Yes, they cannot find structures, but genetic programming is specifically designed to find and build structures. So this could be one of the areas that genetic programming is very powerful in. And as I said, for any, if you want to build an equation, for example, for your engineering problem, you don't want to have a mathematical program or black box system for modeling your data. Instead, you like to have a very closed form solution or a very simple mathematical solution, which we have it in most engineering codes. Yes, we try to put a difficult problem into a simple mathematical equation. So for those problems, I also highly recommend genetic programming.
Sir, there is a question from the participant. Hello?
Yes.
Sir, which are the algorithms which works better for multi-objective, non-convex, non-linear optimization?
So this is not, there is actually theory in evolutionary computation area that say you cannot find a simple algorithm for one to outperform others in one class of even problems. So we usually try to narrow down some of the methods and then try those methods into the problems. For example, I saw an algorithm that and I studied when I can bring it up, compare 18 different techniques, which is for a nonlinear and non-convex problem. So you can, if you look at the results, it's not like one single algorithm can outperform others in all cases. So we can say, for example, this algorithm out of these 20 cases maybe outperform others in 5 cases, but there's no one single algorithm can outperform all others. But specifically for the problem you mentioned, I really refer you to the study that I shared. So we compared 18 different algorithms, and you can maybe select the top 3 or top 4 and apply those into your problem. It could be one way of maybe reducing all those costs and finding the best algorithm out of all other existence.
Sir, I want to ask one question, that how this genetic programming will helpful in electrical engineering, like lightning protection or power system analysis. So anything, if you have explored this, please advise us.
These are not my area of expertise, and this is a very general question. But if you have a data and you would like to build a mathematical model, I can say explicit model, I highly recommend you to use genetic programming. So, for example, you have a prediction model, you have some data and you want to predict something out of it, or you have some data and you want to make a classification model. So in those cases, traditionally, genetic programming can work like others. But specifically, when you need to have a simple solution and when you need to have a closed form mathematical solution for your data, GP can help you. It doesn't matter if it's in electrical engineering, if it's in chemical engineering, if it's in environmental engineering. I've done research in medical problems, biomedical, chemical, civil, environmental, mechanical, and all those areas it could be applied. There is no limitation.
Thank you, sir. Thank you.
Sure.
Sir, can we use genetic programming in computer vision problems?
Actually, there is a very good question. I haven't done that, but actually there is very successful study in 2018 that people try to use genetic programming for game. They try 50 different games and they compare GP with deep learning, etc. And actually GP came the best out of that study. So even MIT Technology Review talked about GP a lot at that time and said it can even outperform deep learning, and it's on the wing, and it's could be one of the future breakthrough of AI. So there are some very good and successful studies in this area, and I can refer you to those studies if you are interested. But for sure, it's capable of doing that.
I have a question.
Sure.
What kind of optimization algorithms are best suitable for what kind of problems? Is there any guide to that?
Very good question. I haven't seen any studies on this, but there are some rule of thumb. that people can give you some, because you cannot systematically do that unless you do a very, very huge study, which may take years of simulation. But for example, if you give me a problem and say we have, I don't know, discrete variables, we have constraint, we have rotation, we have different features or for our problems, I can narrow down some of the algorithms and say, okay, probably these 2 or 3 are the best for your cases. But as I said, you cannot see any study can say one single algorithm can, or even multiple algorithms can come up as the best in all cases.
So one more question. What are nature-inspired algorithm and how to identify natural algorithms?
So a natural algorithm simply try to mimic the natural phenomenon. Yes. So, for example, the bird has some swarm behavior, or fish has a school of fish has a swarm behavior, or particles in physics has some swarm behavior. So we can try to mimic all those behaviors into the computer programs in order to find the best, optimize one or more objectives. So that's what generally happen in nature-inspired algorithm. So if I want to say in all computational algorithm, we want to use different source of information. Yes, for example, in optimization, we use derivative, use Haitian matrix, or this kind of information. Yes, in order to find optimization. So if we don't have access to those information, we can use other source of information like swarm information, or evolution. Information can come from evolution, or information can come from physical phenomena. So these are the tools in order to create different sort of information in order to solving a problem. So if you look at a phenomena and said, okay, it has some innovative ways of looking at problems, it can give me some new informations. It could be one nature-inspired algorithm. Like, for example, for marine structure, people try to inspired from fish sensors in order to place sensors on their submarine structure, etc.
Excellent talk, Professor Amir. My question is about the possibility to apply these algorithms to predict a pandemic or epidemic of this nature. Touch wood, the planet Earth won't come across this plight again. Given the fact a lot of data that could have been harnessed by Apple's and Google's during the early flights from Wuhan. What's your take on how well the Australia has managed, and how do you think the algorithms of mobile data about a passenger's occupancy in a flight relative to other passengers for analysis of possible contact and then prevention of the chain?
Okay, so actually this is probably multiple billion dollars question, because the systems of in this in such nature is very, very complex. Yes, so we have different countries, different cultures, very, very few datas, and if you want to use mobile data, for sure it's a very, very complex system. And also it's change even city by city, yes, state by state, country by country. So it's not an easy problem, but generally, if we can develop, let's say, data-driven model or machine learning model based on all the data we have gathered up to this point for number of cases, for stringency, for economic impact, or if we have all these models, we can simply use evolutionary computation in order to find the best trade-off between all these algorithms. So, for example, the model for, as you said, Australia may not work for countries like India. We are an island. You are bordered with several different countries, or you may not be able to stop all the borders, but here we will be able, because economic situation are really different. So yes, there are so many factors involved, but people trying to solve those problems. There are some lack of data, there are some experiences. We are learning from those data, from those measurements, from those policies. Some of them seem very effective, some of them seems not effective at all. Some of them seem effective for one country, but not effective for another. So these are the things that people trying to sort it out. Actually, for that competition, in X Prize competition, we clearly mentioned we cannot create a model for even each region or each continent. We should go country by country, or even we should go and change the policies city by city. And even for each city, you may change the policy during the time. So this is, I can say, very complex problem, but that we are getting there. And it was a first experience, yes, during the modern era. The last experience of such pandemic was come back to about a century ago. So, yeah.
Thank you, Professor. With the permission of the chair, and that's one more question. The application of fusion of sensors for precision agriculture. Have you tried some of these evolutionary computational intelligence techniques?
Actually, very good question. So for fusion, we haven't done that much research. You need using genetic programming. I myself actually recently published two deep learning algorithm in agricultural engineering in IEEE, but in most cases we try to build IoT networks and then apply simply deep learning to fuse all those data and extract data from those systems. But for GP, for sure we can do that. One problem of GP is if you are not really familiar with the system, it takes time. People are more familiar right now with deep learning or other machine learning techniques, and there are very good packages out there. Yes, most people try to apply those algorithms. They do not try to develop a system. So for sure we'll go out there. These are the very good topics for research, but for application like agriculture, as you said, if we want to maybe develop one GP-based fusing system, I myself, I haven't done that and I haven't seen, but probably if you search, you may find some studies or there may some ongoing research in this area. I won't be shocked if I see those.
Professor, are you welcome to do collaborative research with Indian intellectuals, professors, or other industry professionals?
Yeah, of course, I would be very happy to, and I would be happy to keep in touch with my friend out there, and for sure, if there's any good opportunities, I would be happy to collaborate. I hope this situation, this pandemic situation, resolved. We can commute. I really like to come back to India about a year ago, but it seems for the near future, I won't be able to even travel outside Australia. So this is right now the situation, but for sure we can connect through email or like these online events, and it would be my pleasure.
Thank you very much, sir. And it's well attended by around 700 participants. Thank you very much, IEEE ITSO.
I really thankful of organizer.
Shukumar sir?
Ah,
Yes, sir.
So can we ask another question?
Yes.
yes, sir. Yes, sir.
Professor Gandomi, this is Professor Dev from IIT Kharagpur.
Oh, yes.
I was just wondering, what is the potential of genetic programming for real-time application?
Yes, you are from IIT Kanpur?
Kharagpur.
Oh, okay. I actually have colleagues who came from Michigan State from IIT Kanpur. Kalyan Moidev actually is
Yes, I know.
one of the biggest figure, yes, in evolutionary multi-objective
yes, I know.
optimization. His family also Dev. So I forgot your question. Sorry.
My question was potential of genetic algorithm for real-time applications, for real-time usage, online usage.
Yes. Actually, it's another good question I heard today. I'm really happy for this question. So, as I said, one of the challenges in genetic programming is it takes time to be trained. So, if you want to use genetic programming for online, the best strategy is you develop the model first time, and then next time you try to seed the current model for the next state. So for most cases, most machine learning, you cannot seed the algorithm, yes? But for genetic programming, you can seed the next problem using the current model. So this is one way of using genetic programming. And for sure, if your problem is not super complex, you can always take advantage of this cloud system and train your model very quickly and use it for online system. This has been done. There is one package from Cornell, I think. I forgot the name. Yes, there are some available, and there's one from MIT, I think, using a cloud-based system for very quick and online GP modeling. So there are some research out there, and for sure it's possible. But again, I say it's related to your problem if it's super complex. Yeah.
Okay, thank you.
Sure. Thank you.
I have a question for you.
Hello?
Yes, sir. Yes, sir, please.
Sir, while designing a new genetic algorithm or evolutionary algorithm, what are the aspects do we need to consider?
Sorry, I didn't hear the last part of your question.
What are the aspects do we need to consider while designing a new genetic algorithm?
So there are, I should say, if you want to develop one optimization algorithm in general, not genetic algorithm. So genetic algorithm, one class is already developed. You can only maybe optimize some aspect of it. But if you want to develop any nature-inspired algorithm, you need to find a trade-off between local search and global search. So we call it exploration and exploitation, which means there should be some trade-off in order to look at this algorithm does is try to find a way of
Hello,
Hello?
Professor Amir. Professor Amir? Yes, sir. Hello, Shivakumar sir.
Conclude ಮಾಡದಾ?
అవును sir, ಮಾಡೋಣ sir.
Okay. Finally, thank Dr. Amir H. Gandomi, Professor, University of Technology, Sydney, for giving a wonderful talk on international that webinar on evolutionary learning and its engineering applications. On behalf of the Institute and behalf of all the participants and the IEEE, thank him for giving the wonderful talk on the evolutionary learning and its engineering application. Thank you, sir. Hello, sir.
Hello, Professor Amir. I think he's not audible, sir. He's not audible. Is there?
Could you hear me now?
Yes, yes, Professor. Yes, Professor.
Yeah, I think I was muted by someone.
Yeah. Okay. Okay.
Yeah, so,
thank you very much, sir, for accepting our invitation and giving the wonderful talk. It's a very much informative, and the participants were happy with the attention of the queries by you. You have answered all the queries, sir. The participants were very happy.
I should thank you for having me at this event. It's really my pleasure to see you all, and I'm happy that people.
And in this pandemic situation, it's a very relevant topic. Hello?
Hello?
Hello, sir. Thank you, sir.
Yes, yes.
Thank you very much. We'll be in touch with you, sir, for further collaboration.
We are very happy to collaborate in future also, Professor Amir.
Of course, I would be very happy to.
Okay.
Thank you.
Thank you.
Also, I thank the office bearers of IEEE Bangalore section and IEEE Mysore subsection. Thank you, one and all. And also, I congratulate Dr. Parmeshachari, who has organized this event and is also the chair-elect of the IEEE Mysore subsection. Congratulations, sir.
Thank you, sir. Thank you very much. Thanks for the support for organizing this event under the IEEE student branch GSSS IEEE.
And also, I thank all the participants for participating in this webinar in huge number and for asking the highly relevant question to the resource person for this webinar. I thank one and all.
Thank you, sir. Thank you very much.
As we come to the end of today's session, I now request Ms. Lakshmi Prasanna to deliver vote of thanks.
I, Lakshmi Prasanna, on behalf of IEEE Student Branch GSSS IEW, would like to extend gratitude to Dr. Amir H. Gandomi, Professor of Data Science and an ARC DECRA Fellow, Faculty of Engineering and Information Technology, University of Technology, Sydney, for accepting our invitation and sharing your knowledge with us. I thank you, sir.
Thank you.
I cordially thank our Honorary Secretary, Srimati Vanaja B. Pandit Ma'am, Sri R.K. Bharat Sir, Managing Committee Member and CEO, and Srimati Anupama B. Pandit Ma'am, Administrative Officer, GSSS, who have been a pillar of support. I take this opportunity to thank Principal and moderator of this webinar, Dr. M. Shivakumar sir, for being the guiding light to all of us. Thank you, sir.
Thank you. Thank you.
I thank IEEE Student Branch Counselor, Dr. Parmeshachari BD, Honorary Secretary, IEEE Mysore Center, HOD Department of TCE, GSSS, for his guidance and encouragement in making this event happen. I thank you, sir.
Thank you.
I would like to thank Dr. Manjula Ji, Mr. Kirti Kumar M, and Mistress Naina CG, coordinators of this webinar, for the support they have rendered in conducting this event. Thank you, ma'am and sir. I thank all the student participants of this webinar. Hope the knowledge gained from this webinar will lay path to many young minds. Thank you, one and all.
Ms. Lakshmi Prasanna. This is Mamta M, the Master of Ceremony, signing off.
Thank you all. Thank you, sir. Thank you, Shivakumar sir. And
Thank
Professor,
you. Thank you, sir.
Professor Amir, thank you.
Thank you, Parameshachari, for inviting and having me.
Yes, sir. Thank you. Bye-bye.
Bye-bye.
Bye-bye. Bye-bye. Take care, sir.